Welcome back from break. So now we are going to be understanding, okay, how amino acids actually behave when they are forming a protein or how they behave chemically. The first thing that we must need to establish is that amino acids are stereoisomers. So the majority of the amino acids, with the exception of glycine, because they have one or more chiral centers, they can be found in different stereoisomers. What you see illustrated in this slide on the right side are the structures for the enantiomers of two particular amino acids. On the top, you see alanine, and on the bottom, you see cysteine. So when it comes to the stereoisomers that are found in amino acids, understand that in nature, for the majority of the amino acids, the L conformation is the one that is the most common, okay? And remember that this L and D conformation, which I introduced to you guys, when it comes to sugars, just establishes the positions of the different substituents around the carbon that is chiral, okay? So in the case of alanine and cysteine, understand that in these molecules, because they only have one chiral center, the carboxylate needs to be on the north, so on the top. Then the side chain needs to be in the bottom, and in the middle is what we have, the ammonium and the hydrogen. So if the ammonium group, the NH3, is on the left, that is the L configuration for your amino acid. If the NH3 is on the right, that is the D configuration for the amino acid. For those of you that actually take maybe amino acid supplements as part of your, health regime, you will see that when you look at the food label for the amino acids, it will say L blah, 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 because the majority of the amino acids that we see incorporated in proteins are going to be the L stereoisomers out of the pairs of enantiomers that actually exist out there. Now, another thing that actually affects the chemical structure of amino acids is actually pH. And as I mentioned to you guys earlier today, when it comes to the amino acids, we know that it has an amine and it has a carboxylic acid group. But because of the pH of the blood is around 7.4, then at those pH conditions, then the ammonium becomes protonated and the carboxylate becomes deprotonated. That's why we have a carboxylate group and an ammonium group, okay? Now, let's understand that for every amino acid, we have what is called the isoelectric point, okay? And the isoelectric point, which can be calculated, but I'm not going to illustrate in this class how do you actually do the calculation, because that requires an understanding of acids and bases that we didn't discuss in chapter 10. But understand that the isoelectric point is going to be specifically the pH at which, if your amino acid has charge groups, these charge groups are going to balance each other, and the amino acid overall is neutral, okay? So understand that the isoelectric point for a big number of amino acids is going to be 6. So a value of 6. Isoelectric point is also known as the PI. So for many amino acids, both polar and non-polar, okay, the isoelectric point is going to be 6.0. So what does that mean? Since my isoelectric point, and like I said, isoelectric point can be calculated, but in this class, we're not going to do it. Here, we just are going to visualize, if I know the isoelectric point, if I know the pH value, how is my amino acid going to look like? So, because the isoelectric point for many non-polar and polar amino acids is 6, what that means is that if you put that amino acid at pH 6, what happens to your amino acid is that the carboxylate portion of the molecule loses a proton, so it becomes the carboxylate. The amino side of your amino acid grabs onto a proton, it becomes ammonium, because we have a positive 1 and we're adding it to a charge of -1. That means that the overall charge of your amino acid at its isoelectric point is going to be 0, because the ammonium formal charge is canceled by the oxygen formal charge. So understand that the isoelectric point always is given to you, because that is something that already has been calculated for every single amino acid. So again, if your PI is a value of 6 and your pH matches that value, aka pH of 6, this is how your amino acid is going to look like, okay? So what happens if now I have variations of pH going from the idea that I have the isoelectric point for an amino acid? Well, what happens at this portion is that now structurally, we're going to see a few changes, and it's mainly going to be in the concept of protons being present in the molecule. So we're going to explore, as you can see, where your pH value is below your isoelectric point. So again, alanine has an isoelectric point of 6. So what happens to the molecule of alanine when we put it in pH that is lower than an isoelectric point? Because when we are lowering the pH, means that we're going to have more H plus around. And then the only portion of the molecule that can grab onto that positive proton is the oxygen. Then what that means is that the oxygen becomes protonated. So again, if you know the PI and the pH given is below the value of PI, then your carboxylate area becomes protonated. Your ammonium area remains positive. So this is like saying +1 plus 0, because you can see that now we don't have a formal charge in the carboxylate side. So the overall charge of the molecule is +1, okay? Let's look at what happens if now we change the pH for the particular amino acid to higher than the isoelectric point. So when we go to pH values that are higher than the isoelectric point for our amino acid, that means that at higher pH, we're going to have more OH minus. And OH minus is going to be a base. Now, What portion of the molecule gets affected? The ammonium. Because now it's going to lose a proton and it's going to become an NH2. When the nitrogen loses a proton and it becomes NH2, it becomes neutral charge or zero. It doesn't have a formal charge, or it has a formal charge. I should say it's a formal charge is 0. So our nitrogen is 0 charge. Our oxygen will remain the same, because when you're under basic conditions, or when you're a higher pH where you have more OH around, the O is going to be happy under those conditions. So it's going to remain -1. So your overall molecule is -1, okay? So understand that this whole process of isoelectric point, it is an important feature of amino acids that we utilize it in the laboratory in order to separate amino acids from each other because of the different protonation and different charges that they will have. Or another use is to purify proteins. So we can separate protein samples by fluctuating their pH and taking into account that now overall my molecule is going to have a different charge, and I can separate it from the sample that I'm studying. Any questions when it comes to the isoelectric point for an amino acid? At this course, the important thing that you guys need to know is if I'm giving the PI value and the pH is the same number as my PI, this is how my molecule looks like. It's going to have a 0 charge. At my, if I'm given the PI, if the pH given is below the pH, then my molecule will look like this. Overall, it's going to be +1. Again, if I'm given my PI, if I see that the pH is higher than the value of the PI, then my amino acid is going to look like this. Great. Then let's move on to the next concept, which is these amino acids, as I mentioned when I first introduced what is a protein, are going to be linked to one another to form a polymer, and that polymer is what makes a protein, okay? So when the amino acids come together, they come together through chemistries that you guys have already explored in chapter 14. So the primary structure of a protein, which is the sequence of amino acids, in a protein actually come together to form an amide bond, okay? So an amidation reaction happens inside the cell, okay? When you have 2 amino acids that are coming together to synthesize this protein, okay? In chapter 17, we're going to actually see the different machinery that is utilized inside the cell to accomplish this amidation reaction. But for now, when you have 2 different amino acids coming together, all what we're doing with it is that we are linking the carboxylate side of one amino acid with the amino of the other, okay? And you can see that through an amidation reaction makes an amide bond. And that amide bond is called a peptide bond, okay? Now, overall, how does this happen? We are going to combine the oxygen in the carboxylate with specifically 2 hydrogens in the amino. So whenever we combine an oxygen with 2 hydrogens, that's what makes water, okay? So as we saw before, this is an amidation process. It's just that now we have a carboxylate and an ammonium coming together. And nature does this so beautifully because, trust me, you guys, we don't need to be taking these two things and heating up the system. We actually have biomolecules that are assisting into making this functional group. Now, if you're giving a peptide, understand the pH is not always going to be 6.0 when it comes to this. In the laboratory, you can fluctuate it to whatever your need. What I'm illustrating here is that the majority of your non-polar amino acids and some of the polar amino acids are going to have a single isoelectric point, which is 6. So in the laboratory, it depends on what you're trying to do. You may leave it at pH of 6, or you may change the pH to let the amino acid behave the way that it's going to behave at that pH, because it's a little bit more complex for certain polar amino acids and acidic and basic amino acids, because they have multiple isoelectric points. So for now, this is just a technique that is utilized to purify a sample. So it's not always 6. It depends on what you're trying to do with your sample. For example, in the laboratory, we used to, when we were face-to-face, do a lab in which we give students a sample of fat-free milk. And then we, utilizing the concept of isoelectric points, we will acidify the milk in order to isolate the casein protein out of the milk. Just taking into account that when you acidify, the casein actually forms a precipitate, then you can actually isolate the casein out of fat-free milk. And then in the liquid portion, you leave whey, other proteins, you leave the sugar. So it was an interesting lab that we used to do. Again, utilizing the concept of isoelectric point. So continuing on, as I just mentioned, when it comes to the primary structure of proteins, understand that they are going to be given to you in a sequence like this, okay? Let me just add the formal charge of nitrogen here. So this is a small peptide that has 4 different amino acids in it. Remember, a protein, because of the size of the proteins that we know out there, are known to be at least 50 or more amino acids, and they must have a biological activity. That's what what is considered a protein. Typically, if anything is smaller than that, we call it a peptide in biochemistry, okay? But again, this is a small peptide of 4 amino acids. When we look at the structure of a given peptide, and this one is given in condensed form, there is always a pattern that needs to be established, okay? The pattern that needs to be established is that whenever you're given a sequence of amino acids, it's always going to start with an NH3+, unless you start with proline, okay? And this is called the N-terminus, because it is the ammonium side. This is called the C-terminus, because it is the carboxylate side in your peptide, okay? So every time you are given a particular peptide, understand that you're going to have alpha carbon, amide, alpha carbon, amide, alpha carbon, amide, alpha carbon. Then if you see a carboxylate, your peptide is done. Next, you can actually say, this is the side chain out of my alpha carbon. If I look at my list for amino acids, a CH3 side chain represents alanine, which is, this is the 3-letter code. When you have a CH2 bonded to a CH, bonded to a CH3, bonded to a CH3, that is leucine. A CH2SH, that is cysteine. A CH2CH2SCH3, that is methionine. It is important that you know how to find the different side chains, because this is going to lead to tell you what are the amino acids in the given peptide, okay? I forgot that I included here, but I put in the chat a link to an image that has the skeletal forms of the amino acids. I also included one on the slides, okay? Because you guys will see in the chapter quiz that the peptides that I give you, the side chains are given in skeletal form. So I want you guys to be able to find them. So let's actually practice how to identify, because this is something that you guys need to know how to do for the final, and it is also in the chapter quiz, okay? How to define what are the letters that are found for the amino acids that I have in my peptides. And for me, this is one of my favorite things to teach when it comes to biochemistry, because I think it is very entertaining. And I make it more entertaining because one of the things is that when you look at the 1-letter codes for the amino acids, you can actually spell words. So you guys will see in the chapter quiz and also in the exam, and please don't try to guess the word, because that has gotten students in trouble in the past, that they're like, oh, the word is blah, 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 and then they miss a letter, they misspell it. Please go with the letters that are here and discover the words that I actually put in here, okay? But understand that in the homework, I actually did different ones, okay? Or it's going to be a phrase, but it's going to be, again, words, what I put as messages in the peptides. For me, it's always fun when it comes to the holidays. I have friends that are still, you know, active researchers in biochemistry, and they always have like a Merry Christmas spelled with peptides card, or peace spelled with a peptide. You can spell teacher because you have all the letters for teacher. And so anyway, it's very entertaining. But let's actually do a problem so you guys see how we work these out. Let me paste here the amino acids. It's going to be kind of small, but I'm going to do my best so you guys see how we work these problems. Let me zoom in. So the first thing that you guys need to learn how to identify, okay, is that NH3 portion. This is your NH3. Unless the first one is proline, then it's going to look like an NH2. And you know that you have proline because you can see that proline, the nitrogen, proline is right here. The side chain is connected to the nitrogen. That's why it's an NH2. You guys see it Let me move this to the side. So that's how proline looks like. You guys can see it right here. So I know that this word starts with a P. Okay, because that's proline. Then remember that we're going to have alpha carbon, amide, alpha carbon, amide, alpha carbon. So this peptide has only 3 amino acids. Okay. So what are my amino acids? Here we have a CH2OH. If I go to my list, CH2OH is serine. The 1-letter code is S. Okay. Next one. CH2, CH2, C double bond O, O minus. CH2, CH2, C double bond OH. Okay. So remember, I show you the protonated, you're looking for that. That's the carboxylic acid. So the next letter is E. For those of you that are like, where are you getting the letters? Look, serine, ser, S. Glutamic acid, glu, E. So I'm getting the 1-letter codes. Next one. CH, CH3OH. That is this one. CH, OH, and CH3. So that is threonine, and the 1-letter code is a T. So this peptide, spell the word set. Let's move on to this one. I start with an NH3. And you can see the C double bond O. Okay. I want you guys to take a minute and put on the chat, how many amino acids do I have in this particular peptide? Again, remember the trend, alpha carbon, that's where I have my side chain, then amide, alpha carbon, amide, alpha carbon, amide. So take a moment and let's put on the chat, how many? Awesome. I see that people are getting the hang of it. I'm telling you, it's fun, you guys. Alpha carbon, amide, alpha carbon, amide, alpha carbon, amide, alpha carbon, and then the carboxylate. Okay. So I know that the amino acids are fairly new to you guys. Okay. So this is in CH2. With this ring system. So I know that this is a non-polar amino acid. So that is this one. Okay. That is tryptophan. Tryptophan, the first letter. So the 1-letter code for tryptophan is a W. Next one. CH, CH3, CH2, CH3. So it's like a butyl, that's going to be a sec-butyl group. That is this right here. So as you can see, that's isoleucine. So it's the letter I. Next one. CH2, C double bond O, NH2. CH2, C double bond O, NH2. That's asparagine. And lastly, this is a CH2. That is glycine. So this peptide spells the word wing. Okay. How many? See, don't guess. Don't guess. That's what happened. Like when I teach the semester of biochemistry, the students are like, Dr. Luz, I don't know why I did so bad because I guessed at the words. I was like, never guess. Go with the letters. Like the peptide is telling you what to define. So please don't guess, you guys. And then sometimes I put words in Spanish too. I remember what was it? I think fall of 2020, when I was doing 104, I did familia. And then people were like, oh, look, she put family. And I'm like, yeah, but I put family in Spanish. So then people were like, oh, no. Because again, familia and family don't have the same number of letters. So the peptide will look different. Because if you have family, then the tyrosine is going to be the last one. But then in familia, because you end with an A, that's going to end up in an alanine. So please don't guess, you guys. Go with the flow. Let the peptide tell you what is the correct, word that is in there, the right code. Okay. They're fun. I don't know. Use them on your friends or your siblings. Cousins, I don't know, like write up, don't use it on your parents or tias, because they're gonna be like, this kid, look, going to college, putting up all these structures in it. I don't know what it means. But at least my older brother is a chemist, so I can just send him these things, and he's like, you and your biochemistry, because he studied chemical engineering. So for him, he didn't actually like organic or biochemistry. He's more of a numbers person. So I sent him peptides, and he's like, can you just send me a normal email? And I'm like laughing. Anyways, so let's go through the last one. There's actually peptide jewelry, you guys. I'm telling you, I'm passionate about this stuff because I find it fascinating. So people just like put messages on jewelry, and they put a peptide and then they sell it. I was like, oh, that's kind of cute. Although you cannot spell like love just because there's no O in the one letter codes, but there's other words that you can spell. Anyways, how many amino acids do we have in this peptide? Let's put it in the chat. Excellent. I see the 7 being populated. So we have 1 amide, 2 amide, 3 amide, 4 amide, 5 amide, 6 amide, 7. Those are my 7. Okay. So let me see. It's going to be a little bit on the hard side, but do your best, you guys. Let's define what is the secret word that is in this peptide. So I'm going to give you guys a couple of minutes. And when you're ready, remember, don't guess, but put in the chat. What is the word here? And there's several of these for you guys in the chapter 16 homework. So we know for sure it starts with a P. Because I mentioned to you guys that that first one is proline. So what is the word or phrase that is in the following peptide? Let's put it in the chat. There you go. You got it, Gia. Yes, that is the word there. This is pink hat. Let me continue and highlight this isoleucine. Asparagine. That's lysine. This is histidine. Methyl group. That's alanine. And this is threonine. So again, when you guys are solving this in the final exam, make sure that you guys have this in terms of the structures, because the molecules are going to be looking like this, okay? So make sure that you have that printed table for the amino acids. Any questions? If you're giving a peptide, can we decipher the word that has been given? And it can be in any language. I speak Spanish, English, and French. No, for the for the chapter quiz, I only did Spanish or English. And please don't guess the words. Just go with the letters. Let the peptide guide you. Any questions? Great. So we already discussed that the primary structure for a protein is going to be the sequence of amino acids that make up that protein. There are 3 more levels of structure organization that are present in proteins. And they are called secondary level, tertiary level, and quaternary level. Okay? So what is the secondary structure of a protein? So understand that these proteins, we already saw in their structures that in the backbone of it, we're going to have carbonyls and we're going to have a nitrogen atom that has a hydrogen. One of the things that is known is that when it comes to the secondary structure, okay, which is the 3-dimensional form of local segments of proteins, hydrogen bonds that are going to happen between the carbonyl oxygen atoms and the hydrogen atoms in the amide groups, and this is going to be in the backbone. What I mean with the backbone, you guys, is these. Actually, let me do this one. So in essence, this OH is going to hydrogen bond to, let me do it correctly. Let me use a different color. This oxygen will hydrogen bond with this hydrogen, okay? Now with the one next door, but it actually adopts it depending on the position of the amino acids, okay? Is anywhere between 3 to 4 amino acids down the road. And when that hydrogen bonding event occurs, there are 2 shapes that can be adopted. An alpha helix, which is what you see on the left of the image. And an alpha helix looks like a winding staircase. And the other one is a beta pleated sheet, okay? And that's what you see on the right side of the image. Again, all of this comes from hydrogen bonds that are specifically happening with the backbone of your peptide bond. And these are the 2 shapes that your protein is going to adopt, okay? Now, there's one more level of organization that particularly is going to happen because of the side chains of amino acids that you have in your peptide structure, okay? So the tertiary structure of a protein is going to be the overall 3-dimensional shape. Again, that is going to be specifically caused by the interaction of the different parts of the chain, bends and twists, but the main one is going to be the side chains of the amino acids, okay? Now, when it comes to the tertiary structures, there are a number of interactions that can happen, and I'm going to go through the list by specifically looking at them in this image, okay? Now, one of the things that is known is that these proteins, when they're in the body, they're going to be interacting with the most common solvent that we have in the body. Let's put in the chat, what is the most common solvent that we have in the body? Our body is actually made 73% on average out of it. What do you guys think? What molecule is going to be? Excellent, exactly, agua, water. Our body is made out of water. So these proteins, when they are undergoing all these changes and adopting their structures, they have to interact with water. So one of the things is that parts of the proteins are going to be known as hydrophilic, okay? In these areas of the protein that are hydrophilic, in other words, in love with water, are going to have no problem to be on the surface of the protein, okay? So these amino acid side chains are going to be at the surface of a protein. And if we have things that have OHs, we already talked about the different amino acids. What type of amino acid are those? So where do we find this tyrosines, this serines, which is what we have there? What kind of amino acid are those out of the 4 different types that we learned earlier today? So things that have OHs, out of the 4 types that we learned today, not non-polar. If it's non-polar, it doesn't want to deal with water. Remember, water is polar. Things with the same polarity are attracted to each other. If I'm polar and you're polar, we will solubilize or solubilize. If I'm non-polar, I want something that is non-polar. So the amino acids with OH, where were they classified? Excellent, they were polar. So most of the amino acids that we see at the surface, okay, are going to have polar side chains. So that's why you see tyrosine there with the benzene and the OH. And then you see CH2OH, that is going to be most likely serine, okay? Now, we can also have amino acids that are going to have a hydrophobic interaction, okay? And if they have a hydrophobic interaction, we actually see them at the interior of a protein. Because they're afraid of water. They don't want to be next to water, so they hide inside of the protein, okay? So we know that water is polar. And we can see here that we have phenylalanines. Where do phenylalanines live in terms of the classifications of the amino acids? Check your list. Phenylalanines are not polar. Excellent, they're non-polar. So these amino acids, as you can see here, like alanines, like phenylalanines, that are going to be in the interior of the protein because they don't want to deal with water because they are not polar, okay? They're going to have non-polar side chains. Now, we are also going to have amino acids that are involved in disulfide bonds, okay? And disulfide bonds is one of those reactions that we actually learned, okay, in chapter 14. What functional group can actually be oxidized to form disulfide bonds? Let's put it in the chat. Which functional group do we know that through oxidation can form disulfide bonds? Excellent, thiols. There's only one amino acid that has an SH group as a side chain, okay? And that's going to be cysteines. So whenever we have cysteines, cysteines can form disulfide bonds. Then we have our strongest intermolecular attractive force, hydrogen bonding. As you saw, hydrogen bonding is involved in secondary structure. Hydrogen bonding can happen with the side chain of the amino acids too. And here specifically, we have a hydrogen bond happen between 2 atoms that have an OH, okay? And you have to remember, if my side chains have a hydrogen bonded to fluorine, which doesn't make sense because there's no amino acid that has fluorine in this structure. So mainly we are going to be focused on nitrogen and oxygen. So out of the three elements that can form hydrogen bonding, we're not going to find hydrogen bonded to fluorine at the amino acid level, unless we actually put them there intentionally, chemically, just because the amino acids do not have fluorine in it. None of them, none of the 20 have a fluorine in it. But hydrogen bonding can occur. We also have something that is called a salt bridge. And whenever we have a salt bridge, understand that this is going to happen when we have an acidic amino acid and we have a basic amino acid that are both charged. The reason why it's called the salt bridge, as we learned, is because they're both ionic side chains, okay? We have a full cation and a full anion. So salt bridges are going to be happening with side chains from acidic and basic amino acids that are charged. Okay, so we need to have a full cation and a full anion. Okay, but this is the list of the interactions that can happen at the tertiary level of a structure. Remember, the side chains of my amino acids is what gives rise to all of these interactions. There's one more level of protein organization, okay, that can happen in a number of proteins. Not all proteins have a quaternary structure. In order for a protein to have a quaternary structure, it must have several subunits coming together to make that protein, okay? So in order for a protein to have a quaternary structure, it needs to be different pieces that come together to make that protein. So what you guys see here is a common illustration that we utilize in biochemistry to show proteins, okay? This is what we call the ribbon diagram. The ribbon diagram, you can see all those things that look like curls, those are going to be the alpha helices that are present in the structure. So you don't see the carbons, the oxygens, the nitrogens, you don't see the side chains. You mainly see the secondary structure, and because this is interacting with each other, you see tertiary and quaternary. This is just an illustration. What I want you guys to understand from this ribbon structure for the protein hemoglobin is that it has 4 pieces coming together, 2 orange, and then those 2 that are burgundy. Now, understand that those are colors that were designed. Trust me, these peptides are not going to have these colors. This is just an aesthetic that they decided to do when they published this work, because you can do it any color you want. But understand that the main thing that we're getting out of this ribbon diagram or ribbon structure for this protein is that there's 4 pieces together that are coming together in order to look at the overall structure of hemoglobin. Like I said, not every single protein has multiple subunits to give the largest structure, but some do, okay? But overall, you guys need to understand that when it comes to proteins, we are going to have 4 structural organizations levels. Primary, the list of the amino acids in the proteins. Secondary, which comes from the hydrogen bonding in the backbone between the oxygen in the carbonyl and the hydrogen in the nitrogen. And in that secondary structure, we can form alpha helices or beta pleated sheets. Tertiary structure, which is the interaction of the side chains. And that's what gives the first overall 3D structure for the protein, and then the quaternary structure, which is the subunits that are coming together. Any questions when it comes to the organization of protein structure? And to be honest with you guys, this is very useful because whenever we are in the laboratory understanding protein interactions, or there are medicines that are being designed, they look at these diagrams and they can actually see the interactions of those molecules with the particular protein that you're interested in studying. So all of this is where, again, chemists and biochemists can work together to, design different medicines out there. Since there are no questions, let's now look at proteins in terms of shape. When it comes to proteins, proteins have two particular shapes. They're either globular or fibrous, okay? And globular protein is the shape that the majority of proteins adopt, okay? Globular means that it has a spherical shape. It looks like a globe. Now, globular proteins, since it's the most common, we can see that most of the globular proteins are going to be involved in carrying synthesis, meaning that they're going to be enzymes. They're involved in transport. They're involved in metabolism. They're involved in storage. So understand that out of the two shapes, globular proteins is the most common inside cells. Fibrous proteins, because they look like fibers, they're going to be mainly observed in structures. So for example, hair, wool, skin, nails, they have fibrous proteins. And then you can see here, that's the picture of keratin, okay, which is an important protein that is found in hair, okay, or wool, because you can see the sheep right there. Now, we can classify proteins not only in terms of the shape, as we saw, globular or fibrous. We can classify the protein based on function. And for the chapter quiz, you guys need to know, given a little description, what type of protein are we dealing with? As you can see, all of this is summarized in table 16.1. I didn't print the highlighted study guide, but again, if in the highlighted study guide for the final exam, you guys need to know the classification of proteins based on function, understand that that is table 16.1, so you may utilize it. I don't have my printed version, so that's why I cannot tell you, but make sure, check out the highlighted study guide for the final. But let's talk about this because I know there is a question about the chapter, in the chapter quiz about this concept. So we can see that if my protein is involved in structural components like collagen or keratin, that is known as a structural protein. If my protein function is to make muscles move, okay, involved in the actual movement of the muscle, not that it makes muscles move as a result of, okay, that is known as a contractile protein. If the protein is utilized to carry essential substances throughout the body, that is known as a transport protein. And we learned about an important transport protein in the last chapter, lipoproteins. Remember that that is the one that carries cholesterol and triglycerides in the body. If your protein is utilized to store nutrients, okay, that is known as a storage protein. So the proteins that are in milk, whey, and casein, those are, again, proteins that we can obtain if you eat dairy from your diet. If you don't eat dairy, that's okay. There's other proteins. There's pea proteins, there's soy proteins. That's why if you guys look in commercially, there are a different, there's a wide variety is what I'm trying to say of different protein powders that you can choose from if you have a vegetarian or vegan diet versus if you have an animal protein-based diet. So you can choose whatever suits your preferred diet. If your protein regulates body metabolism and the nervous system, that is known as a hormone. If your protein catalyzes biochemical reactions, that is known as an enzyme. And there's proteins that actually recognize and destroy foreign substances, and those are known as protection proteins, okay? So again, make sure that you verified in the highlighted study guide. If this is a concept that is highlighted, then table 16.1 is something that you're going to utilize on the final. Now, the shape of a protein can always be affected, okay, depending on the conditions that it is exposed to. Some of these conditions are actually very useful, okay? Other ones are actually harmful. So protein denaturation is going to be different treatments that proteins can undergo that affect the shape or the structure of your particular protein, okay? The 5 different types of protein denaturation, okay, that you guys are going to be studying right now include heating, the use of acids and bases, the use of organic compounds, the use of heavy metals, and lastly, agitation. Let's go through each of them, okay? So let me first, because I verbally say it, but let me just write it down, the definition of denaturation. So that's what denaturation is. So let's look at these different denaturing agents, starting with the first one, heating above 50 degrees Celsius. So one of the things about heating things above 50 degrees Celsius is that what you do at the protein level is that you affect the hydrogen bonds, you affect the hydrophobic interactions between the nonpolar R groups in your protein structure. So when we look at the protein structure levels, heating something above 50 degrees Celsius is going to affect the secondary, tertiary, and quaternary. If available, just because quaternaries are not common, of structure. So an example of denaturation of protein is when we cook food, okay? That's why sometimes these are claims. I really do not know the knowledge about it or have the knowledge or actually have investigated, but commonly people think that whenever they eat specifically beef, because that's the one that you can eat less cooked, that the redder it is, the more protein. That's what I've heard, but it in a way makes sense. It's more folded protein, but I don't know how good that can be for your health. I'm just saying that people are just claiming that that's why they like things more on the rare side, just because the protein intake is going to be better. I really don't have a clue, you guys, but I've heard that. Yeah, that's the thing. And then you have a higher chance of bacteria. So that's why I'm like, and then people apply it to other meats. I'm like, don't eat raw chicken. That's not good for you. Or pork. No, Like, don't apply that to all the meats. Like, you need to know where your beef comes from if you're going to eat it rare. I don't know, just because I personally don't do it. I don't know. Yuck to the bacteria. Oh no. Oh, I don't know. I don't know about all that. But for example, for those of you that are going to be going into nursing, many surgical instruments are going to be autoclaved before a surgery, right? But that is a good thing, because you don't want bacteria and other things growing on those surgical instruments, just because that can create an infection. So that's why many surgical instruments are going to be autoclaved to be sterilized. So it's a form of sterilizing objects. Another denaturing agent that can affect the structure of a protein is going to be the use of acids and bases. Acids and bases affect hydrogen bonds between polar R groups and also salt bridges. So that means that they affect the tertiary structure of a protein. Now, where do we see this in action? Well, for those of you that consume yogurt and cheese, basically what is happening is that the milk protein, if you're eating milk-based yogurt and cheeses, the bacteria specifically is going to be producing lactic acid through the process of making the yogurt and the cheese, and that's what is going to denature the milk protein, and that's what creates yogurt and cheeses. Okay. We can also have organic compounds, okay, denature proteins. As you can see, the hydrophobic interactions are the ones that are affected. So we are going to be affecting the tertiary structures of our proteins, and the use of ethanol, isopropyl alcohol to disinfect wounds, okay? Or if you are using that to prepare skin for injections, is because, again, if there is any bug on you or on the area, that is going to basically denature the proteins, and at times that is enough to kill bacteria. So understand that that's why it's done. The use of heavy metals. Okay, so for example, silver, lead, mercury. I hope that nobody is ever affected by this in the world, but sadly, it is true that this is a problem, and it is a problem in this country too. As we know, there are states and there's specific cities in the state of Michigan that have contaminated water that has heavy metal ions. Certain communities have been affected by this, and that's why they're so prone to cancer and other diseases. Now, why is it that you do not want heavy metals or certain metals in your water? Because as you can see, that is going to break disulfide bonds. And if you break a disulfide bond, yes, that's great point, Gia. That's another reason why you have to also check your fish intake, especially if your fish is prone to have high mercury levels. Okay. And that is something that is available online. You can see what are the mercury levels in specific fish. And then there's some that, again, you cannot eat in high amounts, because heavy metal ions actually are going to disrupt disulfide bonds. So they affect the tertiary structure. And remember, this leads to unfolding. If your protein is unfolded, it's not going to be functional. Okay. Let me just put that there. If protein unfolds, it is not active. Specifically, if you have an enzyme and your enzyme is now unfolded, it's not going to work well. So as you can see, mercury poisoning, lead poisoning. The last denaturing agent that can, again, unfold proteins is agitation, okay? But for example, agitation works well in baking, like if you're making meringues or if you're making frosting, it depends on what you're trying to do, right? Agitation, what it's going to do is disrupt the hydrogen bonds, the hydrophobic interactions, and it's going to be stretching the polypeptides, okay? And it's going to disrupt the stabilizing interactions. So basically, in a way, agitation affects the secondary structure and tertiary structure of a protein. But as you can see, in baking, this is a positive thing, because through agitation, we can create meringue from egg whites. You can create whipped cream from cream. And one thing that I have never tried, maybe you guys have tried it, I just saw it the other day in TikTok, and I'm tempted to try it, but I'm a little bit skeptical. People are taking the liquid of garbanzo beans, and you can make meringue out of it. I was very impressed of the consistency. I don't know about the taste, but I guess in vegan cooking, that is one of the ways in which you can create like meringue type, products. But I'm very interested. I was like, wow, garbanzo liquid. It can create like that foamy egg white. I don't know about the taste, but I'll try it. Oh yes, souffle pancakes. You know what? That's one thing that I need to try this summer. I already seen that there's a couple of places that have the Japanese pancakes. I saw Morning Glory down in Little Italy has them. I'm like, has anybody tried those? Those souffle pancakes look so good. Are they good? Oh, it took a while, but that's okay. I'm patient. For good food, I'm patient. Japanese cheesecake is so good. I don't know if anybody has tried that. When I lived in Canada, in Montreal, that was mostly like if you go to Chinatown, like most of the baking places were Japanese. And oh my God, that Japanese cheesecake, so good. Now I'm hungry. I'm sorry. This is the time where I start getting hungry. So overall, these are the different denaturing agents that you guys need to know as part of this course. And we can see in the second column, how does the protein structure levels get affected depending on what are the bonds disrupted. And you can see that in the third column, those are examples. Any questions about protein denaturation? What? Korean pancakes? Wait. I have not heard of those. Where can I find those? Adeline, let me know in the chat where I can find the pancakes.
I've never like bought them anywhere, but you can just like make them, and they're more like savory than sweet.
Oh, okay. Now I'm going to go on Google. If anybody finds a recipe online, please shoot it over email to me about these Korean pancakes. All of food related, I'm interested. I like to explore. Korean food is so good. Whew, so good. Oh, I lived in Canada 4.5 years. I lived in Montreal from I moved there December of 2010. And then I moved from Montreal to California the summer of 2015. Great place to visit if anybody wants to visit Canada. Like if you want to go to Europe, but not travel across the Atlantic, go to Montreal. And it is okay to speak English there, because I for sure made the personal decision to learn French just because I was working in a French university, but it's a great place to visit. Any other questions? Well, this is all for today.